Good evening, ladies and gentlemen. Got another special edition of CP Physics on tap for you. Today, you guys were supposed to work on this whole free body with diagram worksheet thing, and I got a few questions on that. So I checked it out. I told you I'd do a screencast, and here it is. So, good enough. What I expected for you guys to print out was that. And then when I went to Schoology, what you guys did print out was that. So that's probably part of the source of this, because apparently I forgot to click save before I clicked upload, whatever you'd say. So that might solve some of your problems right there. We will get to friction and stuff like that later in next week. We'll probably start that Monday, Tuesday-ish. But for right now, I just want to make sure that we are solid on force diagrams, because those are really, really uber important. The forces that are listed on here, those are the most frequent forces that you're going to experience in this class and, frankly, life. So you should have a really good understanding of those. The ones that you looked at yesterday with your activity and you described them off of the physics website, that's pretty much all of the other ones that we could talk about. So you should be able to have a nice conversation about any instance in the universe at this point in time. Should be fun. So to help us out and to help guide me, I've got a little PowerPoint for you. Normally, I don't use a PowerPoint to talk about force diagrams because they're literally little sketches that you do in order to show the forces acting on something. But for the sake of my own sanity, we're going to go ahead and have a PowerPoint. So, force diagram, what is it? Well, obviously it's a diagram that's of forces. It's also called a free body diagram, called a bunch of other things. It basically shows the important parts of what's going on in any kind of an instance that you're looking at. So, the little description right here of a guy pushing a box across the floor inside of a room type thing, too much info, okay? None of that stuff matters, okay? Well, the only thing that matters are these arrows and the object, okay? Your force diagram is going to show forces. That's it, okay? Nothing matters. Objects, we don't care if it's a box, a car, a duck. We represent them with a simplified shape. Generally, it's either going to be a point or it's going to be a box. I'm a box kind of guy myself. If you're a circle, that's fine. I'm not going to judge you. Now, forces are abbreviated with symbols. You do not list the quantities. So, although it's tempting to say, hey, it's a 10-pound box, we don't say it's a 10-pound box. We say the force of gravity is 10 pounds. We would just show Fg here, or in some cases mg if you prefer, and then we would list the variables elsewhere. Okay. The arrow sizes and directions are approximated. Their sizes are reasonably close to one another, or one is obviously very much larger. So you would have the direction meaning something and the size of the arrow meaning something. Now, this last note that's right there, mass, velocity, and any other information, I would list that on the side of it to keep your diagram clean. It is an acceptable convention to write like the mass of it in here, but when you start doing that, people want to write in other stuff like how fast it's going or something. No. Write those other variables that you know on the outside of it, just like you've written all of the given variables and all the problems that we've had so far. Okay? Now, with that being said, nice little example. Free body diagram of a person pushing a shopping cart. Well, this gets you the idea of what's going on. You got a person, they're pushing a shopping cart. They're pushing with a force of 75. The cart's pushing back on them with a force of 75. Life's good. That's not a free body diagram. There's cluttered info here. This is a free body diagram. This is a force diagram. All it's doing is saying, hey, these are the forces we're looking at. These are the forces acting on it. This is approximately what they are. This is approximately what direction they're acting in. Okay? For a lot of cases, that's literally all you need to know. Couple more examples. You know how I said that you could either use like a box or a circle? Yeah, those are two acceptable ones. Another acceptable one is literally just a dot, where instead of drawing the circle, you just put a dot there. And that's really good for like a baseball. It's easy to envision a baseball as a dot simply because it's round, right? If you spin a baseball, it spins around that point. Well, that point is the center of mass. And so a lot of people, when they're drawing their force diagrams, they literally just show the center of mass. Force of gravity acting down. Cool. That's my baseball flying through the air. Okay. Force diagrams are supposed to be that easy. They're supposed to be a powerful tool that is quick and easy to make, so that way you can quickly and easily analyze your problem. So, for a quick example, my cell phone. I'm pushing it across the table right now. Okay? See how I'm pushing it at constant speed? Well, we got a couple of things going on here. First off, it's very tempting to want to draw the table, to want to draw the cell phone sitting on the table. But that is entirely not needed. Don't do that. Literally, that's my cell phone. That's the car driving down the road. That's the duck on the water. It doesn't matter what it is. So then, thinking about my cell phone, what forces are acting on this thing? Let's see here. I got gravity pulling it downwards. So I always list gravity as force of gravity. You could also say that it is mass times gravity. That would work as well. There is a normal force, you should know that by now, that is keeping this thing from falling through the floor or through the table. I was pushing it this way, so that means I have an applied force applied, and it was overcoming friction in order to slide across the table, so that would be my force of friction. Cool. So that's my cell phone that I was just pushing across the table. Now you can actually break it down and analyze it. Okay? Another thing to think about. I love my baseball activity. Let's think about a skydiver. That's my skydiver, right? They're falling. They have their parachute on, right? So when the skydiver is just falling, their free body diagram looks like this. Ignore wind resistance, ignore everything else. They are falling. They're accelerating at 9.81 meters per second squared downwards. Good for them. Now, later on, they have their little parachute open, right? Yeah. So now they are no longer in free fall. They now have another force acting on them. They have the force of gravity still pulling them down. It's just they have another force of drag, lifting them up, holding them up, slowing them down so that way they don't hit the ground quite as fast. Okay? So both of these are the same object at the beginning. It's just different instances and different force diagrams to show the different forces acting at that time. Okay? Now, with this thing, we could very easily say that this is a 100 kilogram person, and so therefore we could figure out the force of gravity was equal to 980 newtons and blah, 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 blah. But you don't always need to do that. For example, you can just use your force diagram to figure out other problems. Okay? So, if you know, for example, that your car, this will be a top view of your car, is sliding down a hill this way. Gravity is pulling it down the hill that way. What direction do you need to apply a force to hold it back? Well, if the force of gravity is pulling it that way, we need a force applied to resist that holding it this way. Okay? It may seem silly, but it could help you out later on. You could help pull a friend out of a ditch if you understand that. Really simple. Another thing that's a not so simple example. Have you ever noticed how telephone wires, if you look at them, they are not straight across? You ever notice that regardless of where they're at, whether they're high tension wires or whether they are just outside in your normal street, they always have that sag to them. The reason for that is really easily understood if you understand that, well, how to use a force diagram. Because if you look at the fact that this thing is actually made up of a bunch of particles that behave like individual tennis balls. If we expand on that thing, that tennis ball that's there, that's the wire, is being pulled on by the force of gravity, right? But it's actually being supported upwards by a tension force. Now, that tension force going that way has to actually be equal to the force of gravity pulling downwards. We have to break this into components. And there has to be a component equal to and opposite of that to keep the wires from falling. That's why regardless of how tight or what type of wire they are, there's always a sag in the wire because you cannot pull that wire tight enough in order to eliminate that force of gravity. You have to counter it with the sag, with the angle of the wire itself. So those are a couple of applications of force diagrams. I'm hoping that you will be able to draw them and use them very, very quickly and effectively. Most of the work that was turned in from Schoology looks like you got this part pretty okay. Just make sure we're not like writing these things out. Use symbols in your force diagrams. Do not write out what it is, write the quantities. We're not dealing with that here. If you know what the quantity is, you would say, the force of gravity is 100 newtons. Cool. Don't write it in the diagram. Okay? Other than that, hopefully you're doing well, and I will see you hopefully soon. Take care.